Hello, this is Raj Patel, and today we're going to be talking about heat calorimetry and heating curves. And I decided that today I'm just going to do this one PowerPoint because I noticed that my videos are getting longer and longer. So this is pretty extensive topic. It has a lot of stuff. So I just want to make two short videos. And so this will be the third video or second video of Unit 11, which is all about states of matter. And we'll have one more video to wrap up this unit. And so let's begin by talking about heat. So this is sort of like a refresher because I'm sure most of you know this, that change in thermal energy of a substance causes the change of phase. And so we have the three phases, solid, liquid, and gas. We can always add in heat and if we add in heat, the particles have more energy, so they'll have a little bit more space and they'll flow around. And then if we heat up even more, it'll form a gas and bounce around like this. And that's when you absorb energy to go from solid to liquid to gas. And that's called endothermic reactions, just to remind you, energy is absorbed. Exothermic is the opposite, with gas to liquid to solid. And so you slowly release energy and the particles get closer and closer together to form a solid. And so, just as if water's on a hill, so this is a hill, and then this is a lower spot on the mountain, and this water's flowing down. So water will flow down, and it just happens like that. So just as water flows from high to low because of gravity, uh, and a difference in the height, heat always flows from hot to cold. Always remember, hot to cold. Just think of how water flows down a river or downwards because gravity pulls it down. So energy enters your hand from a hot stove because the stove is hotter or warmer than your hand. So the heat goes from hot to cold and goes to your hand. But if you had an ice cube in your hand, the energy passes from your hand into the ice because your hand is warmer than the ice. So always remember, heat flows from hot to cold. And heat is thermal energy transfer due to temperature difference. And always remember the difference between heat and temperature is that heat is the measure of thermal energy transferred, and then temperature is the average thermal energy of the particles in like a group. So like if we measure the average, it's like the temperature that they're mostly at. And then thermal energy is literally just all the energy of the particles. And so just know the three different types. And here we have another thing. So we have a hot stove and we have two pots of water. And so we heat up the stove, so the same amount of energy is going to each bowl. But notice how much the temperature changes from this little group than this big old pot here. And so pretty much the same amount of heat is added to each container, but the temperature of the container with less water increased more. And why would why would a smaller amount of liquid or water be easier to heat up? And this is pretty simple. And so pretty much if we have less water or less of a substance, this heat can go to every single substance with more heat goes to each substance or more energy. But if we have a lot, we have to spread this heat out evenly, and so heat goes to everything in this pot evenly. So because there's more water, all the water gets some heat, but it doesn't change it as much as this one simply because there's more water to heat. And now we're going to be talking about specific heat. So we're going to shift topic, sort of. So water in food holds 4 times the energy as an aluminum pan. And it's important to know that different substances have different capacities for storing energy. So if you remember, or even from everyday life, you notice that like water stays very warm for a long time. Or when you're freezing water, the exact opposite, it takes a long time for the water to freeze because it stores a lot of heat. But if you ever go to like a restaurant and see that, they have like pizza or like, a pie, and after like 5 minutes, you would notice how the pan, what the thing was being cooked in, the aluminum pan or steel pan, it gets very cold fast, and it also heats up fast. So after like 5 minutes, the pan might be super cold or like room temperature, but the food inside is hot, and that has to do with this specific heat, which we're going to talk about right now. And specific heat capacity is the heat required to raise 1 gram of the substance by 1 degree Celsius. So how much joules do we need? And water happens to have a very high specific heat. And so it needs a lot of heat to change 1 degree. And the specific heat for water, by the way, is 4.18. And it's a good thing to memorize this because this is going to be very common on your tests and stuff. So, but most of the time, usually specific heat is given to you, but it's a good thing to remember this. So, this is what specific heat tells you. So if we had 1 gram of water at 14.5 degrees Celsius, we would have to put 4.18 joules of energy into it to turn it to 15 degrees Celsius. So that's what this means for every gram. So if we have 100 grams, we have to put 100 times this to change it. And now we have we're going to talk about a formula pretty soon. And so notice the specific heats, and so 1 gram of water requires way more heat, because look at all these metals. So these metals, look how low their specific heats are. They're less than 1. And then olive oil, which sort of has some water and a little bit of water in it, has a little lower specific heat, maybe half, but still pretty high compared to these metals. So metals, because they have a low specific heat, they heat up and cool down very fast because they don't really store energy. They're so good at conducting that they just let the heat through. And that's why they have low specific heats. And if something has a higher specific heat capacity, that means it'll store heat, so it'll take longer for it to heat up or cool down. And that is why water can absorb and release a lot of heat for a small change in temperature. And delta, by the way, just means change, and T is this temperature, so that's what it stands for. And so again, water has a high specific heat, and now we're going to talk about why. And we're going to link this back to what we talked about earlier on the last video, IMAFs. And so this has to do with all about IMAFs. So aluminum compared to water has a lower specific heat because aluminum's atoms just vibrate in place. But water has 3 atoms inside one molecule, so water can soak up or store a lot of energy in intramolecular movements and intermolecular attractions, or H bonds, without changing the temperature. So pretty much when you heat up water, it can vibrate or stretch these little bonds like this and this. We can stretch the bonds, or it can rotate. So these are all examples of intramolecular because it's just one molecule. So all these molecules can vibrate or stretch or rotate. And also, it's not included in these pictures, but the intermolecular attractions, or IMAFs, or H bonds, hold them together. So this heat has to break these bonds and has to overcome the stretching and rotating and vibrating to change the temperature of the water to make it move faster. And so this is what heat does. So it pretty much, in aluminum, it just makes the atoms vibrate a little bit more, and then they become heated. But water can vibrate, stretch, or rotate the little atoms, and also there's H bonds that connect them, so that prevent it from heating too much, or he has to break those. And again, that's why water has a high specific heat. And so here we're gonna use a formula for calorimetry, or the measure of heat transferred. And so the formula is Q equals MCAT, or Q equals MCAT, or no, delta T, sorry, delta T. And delta just means difference. And so this is going to be given on the exam, so no need to remember this, but if you ever need to remember it, think of Q equals MCAT. And Q equals heat in joules, M is mass in grams, C is specific heat is in joules per gram degree Celsius, and specific heat for water is usually always given, but it's 4.18. And then temperature, or delta T, which is change in temperature, is measured by final minus initial. So always remember to do final minus initial so you get the right sign for Q and for the heat. So always do final minus initial to find delta T. And so now we're going to do a problem. And so how much heat is needed to warm 500 grams of water from 25 degrees Celsius to 100 degrees? So we have our formula, Q equals MCAT, so we need to plug in everything, and so we're solving for Q, so we literally plug in everything and multiply. So mass is right here, 500 grams, and specific heat is given to us, so C is 4.18, and then to get delta T, we subtract final minus initial, and we get 100 minus 25, which is 75. So we just literally multiply all these together, and you could do 500 times 4.18 times 75, and then we would get 157,000 joules of energy would be transferred to do this. So we would need 1,500. Okay, sorry, 157,000 joules to change the water, 500 grams of water, from 25 degrees Celsius to 100 degrees Celsius. And now we're going to talk about matter containing heat in terms of kinetic and potential energy. So it's incorrect to say that matter contains heat, because heat is always moving, and matter just contains internal energy, or kinetic energy and potential energy. And it's always important to know that heat is always transferred, so heat is lost and gained. It's not always inside something. So matter doesn't really contain heat. Heat is just the surrounding, and whatever happens to be, the heat goes in and changes the temperature or energy. So it's never really contained. It's always moving. And so here we're going to talk about eternal energy. And so internal energy is made up by kinetic energy of moving molecules. So these whole dots here, if you can't see them, behind it there's just a ton of dots. So each one is a molecule. So kinetic energy could be measured by the moving molecules or the moving atoms in a molecule. So just like we looked at the water molecules inside each atom moves a little bit. And so this can also represent kinetic energy. And then potential energy, which makes up a lot of energy, is stored in the attractions and bonds. So potential energy is stored in bonds and IMAFs. And again, we talked about internal energy is total of all kinetic and potential energy. And gases have mostly kinetic energy because they don't have really IMAFs because they're moving so fast they don't attract to each other. And liquids and solids have mostly potential energy because they have a lot of IMAFs and they don't really move that fast, but they do move a little bit. So each of them have some of the kinetic energy and potential energy, but it depends on the level. And so now we're going to talk about ice melting and substances changing states. And so ice melts by absorbing heat but without increasing temperature. And how can that happen? So like, how can you increase energy but not increase in temperature? But the change is how much potential energy is changed. And so like the snowman is doing, see, he's melting, but even though he's melted, they're still at 0 degrees Celsius as a liquid, and this is 0 degrees Celsius as a solid. And the difference is potential energy. So we'll look at that on these heating curves. And so this has to do with changing phase, so how it can change. And so here we have a heating curve, and so pretty much if we start out with a solid, we would show this chart, and so temperature is, the kinetic energy of the particles, and then energy input is how much energy we put in. So we start here as a solid and work our way up to gas. And these slanted regions represent the three states of matter. Solid is all the way at the bottom because it's the lowest temperature. Liquid's in the middle because it's beneath gas and solid. And then gas is all the way at the top and continues on and on and on. And then these little lines represent phase changes. So first one is melting and freezing, and then second one between liquid and gas is obviously condensation and vaporization. So, but this is a heating curve, so technically solid to liquid is just melting. So this is melting and this represents vaporization. But if we had a cooling curve, which is exact opposite but arranged so gas on this side and then solids on that side, it would be like another opposite staircase. It's exactly the opposite. So I'm sure most of you understand how it works. And so here we have 0 degrees of solid to 0 degrees of a liquid and 100 degrees of Celsius of water to 100 degrees Celsius of gas. So if it freezes and freezes at 0, vaporizes at 100, it must be water because that's the only substance we know. So you can figure out what material it is if we have 0 at the melting freezing point, or we are given a number here and we're given a number up here. You can figure it out. And so now we're going to ask, so the same temperature during phase change, so even though it's gaining energy, the temperature stays the same, and this all has to do with what's being changed. So this added heat, so normally added heat changes the temperature and increases it like this, these sloping regions. But when we're at these little phase changes, the heat goes into breaking the IMAFs and increases distance or potential energy. So when we're here, the heat that we're heating this water up with, is used to break the little IMAFs attracting these molecules so they can space out more. So the temperature does not change because they don't move any faster. We're just breaking little IMAFs. So that's what happens at these non-sloped areas. So IMAFs are breaking, so the heat is used for breaking IMAFs so the temperature doesn't increase, because temperature is all based off of particle speed, not just the potential energy. And now we're going to look at another curve. So it's exactly the same: solid, liquid, gas, the sloped regions. The leveled regions are phase changes. So we have melting from solid to liquid, boiling is from liquid to gas, and then opposite, condensation, gas to liquid, freezing from liquid to solid. And so now we have these arrows which represent endothermic and exothermic, just as a review. So endothermic, we take in heat. So if we take in heat, we're getting more energy, so we would go from solid to liquid, just like it says, and liquid to gas, because gases have more energy than liquids. And exothermic is the opposite. We're going from more energized to less energized, so from gas to liquid and liquid to solid. And again, those are the freezing points would be below, because below the point would be freezing, and then above it would be melting. Same thing with vaporization. Boiling point would be over, and then condensation point would be below, but we didn't have space, so that's why it's on the bottom. And so now in these regions, like we said, the bonds, IMAFs are breaking, so potential energy is increasing. In these sloped regions, temperatures increasing because heat raises temperature because the particles start moving faster until they get to these phase changes where the heat starts breaking IMAFs. And so remember, think of endothermic as kinetic energy to potential energy. So just think about when you're looking at these, just think about which way endothermic goes. So endothermic goes from bottom to top. So here we have kinetic energy on the slope, and then as we go this way, we break these bonds, so we have more potential energy. So we're going from kinetic energy to potential energy. And then exothermic, it's the opposite. So we take potential energy and we release it as kinetic energy. And so just think about these lined areas. So condensation is going down. So if we start here, we're at potential energy and we go down kinetic energy. But this is just to know, but you don't really have to know this much. But so when you're doing endothermic, you're taking kinetic energy, or just think about it in terms of heat. So kinetic energy is heat, and we store it as potential energy and increase it. And then exothermic's exact opposite. We take potential energy and then release heat. So just think about kinetic energy at heat and you can figure this out. So exothermic releases heat from potential energy, and then endothermic takes in heat into potential energy. And so here's a last heating curve. Again, solid, liquid, gas, and then those are the phase changes. And so now we're going to talk about heat of fusion, which is right here. So the heat required to melt or freeze, and then there's heat of vaporization, which is the heat needed to vaporize or condense. So pretty much condense is just the opposite. So or freeze, which is the exact opposite of heat of fusion. So notice how the heat of fusion line is shorter than the heat of vaporization, and the number of heat of vaporization is larger. And the reason why is it takes more energy to go from liquid to gas than from a solid to liquid, because we have to break way more IMAFs to go from liquid to gas, because gases have no IMAFs whatsoever. So liquids do have IMAFs, so we have to break all the IMAFs, and that's why it takes a lot of energy. But if we're going from solid to liquid, liquid still has some IMAFs, but when we're going from solid to liquid, liquid still has some IMAFs, so we don't have to break off all of them. So that's why it takes less energy, but we still have to break some. So that's why we have a phase change line. And the exact opposite, so like a cooling curve, which I talked about briefly, is just like this. So we have gas on the top, instead on the left side, and then solids all the way at the bottom. So let's just say we had a scenario, we had a gas and we're cooling it down to a solid. This is what you would see. So gas, the temperature goes down. Again, at the phase changes, it's equal, because this time kinetic energy is converted to potential energy is being converted to kinetic energy, and so we go down again from liquid. So kinetic energy is going down. Then we go from potential energy to kinetic energy, and we go down again to solids. And then it's the same exact thing. So heat is being removed, and that follows the same exact rules, like heat of vaporization or condensation is longer than heat of fusion. And so here's a quick quiz to see what you learned. Temperature is directly proportional to the blank of a substance. Thermal energy, vibrational kinetic energy, average kinetic energy, or total kinetic energy. And the answer is C, because temperature is a measure of average kinetic energy. So it takes in all the atoms and finds an average. But when we talk about thermal energy is just a measure of how much the particles are moving. But temperature is average. So just remember, temperature is always average. And so that's the difference between temperature and just thermal energy in general. And so a good way to think about it is, like, if we have a swimming pool and a hot pot of boiling water, even though the hot pot of boiling water has a higher temperature because all the particles are super hot, the pool has technically more thermal energy because there's so many particles that each and every one of the particles has a little bit of energy. So we take the sum of all that energy, it ends up being more than the hot pot of boiling water, even though the pot of boiling water has a higher temperature, because simply there's less water in the pot than a big pool. So that is how the difference between temperature and thermal energy. And so heat is simply another word for A, temperature, B, internal energy, C, energy transferred from hot to cold, and D, thermal energy. So heat is, we've been talking about heat, and heat represents Q in that formula, MCAT, and that's all about energy transfer. So definitely C is an answer, because heat is the energy that's transferred. And there's one other answer. Heat is also thermal energy, because um, because this when we talk about heat, it represents energy, and so energy, or temperature, so, or temperature and motion. So heat is also thermal energy, but it also can be the heat or temperature thermal energy transferred between substances. And so here we have question 3. So this is a calculation problem, so you should get out your calculators, but this problem is pretty easy. How much energy would it take to raise 1 gram of liquid water from 20 degrees Celsius to 30 degrees Celsius? So remember the formula, Q equals MCAT. So just follow along in your head. So we have mass, we have temperature, but we can figure out delta T, and it's liquid water, so we know the specific heat is 4.18. So for every gram of water, we need to increase temperature. We have to add 4.18 joules. But if we have to change that 1 gram of water 10 degrees, so because 20 to 30 is 10, so if you had to do it, you can do 30 minus 20, you get 10. So if we have to change 1 gram of water 4.18 joules for 10 degrees, if you write out in the formula, 1 gram is mass, 30 minus 20 minus 30 minus 20 is 10. So we have 1 times 10 times specific heat of water, which is 4.18. We would get 41.8 because we just moved the decimal one place to the left. So to the right. So we just made 4.18 to the right. So that's how we get the answer. But you can always do the formula if you don't understand this. And so same thing, we have another problem, but we have the same number. How many joules would it take to raise 10 grams of liquid water from 20 to 30 degrees Celsius? So instead of having 1 gram of water, we have 10 grams now. And so if we have 10 grams, that's the mass. And then remember, Q equals MCAT, so mass, specific heat, which is 4.18, and then delta T, which is A and T. So 30 minus 20 is 10. So it's be 10 times 10 times 4.18. So if we move the decimal places 2 places to the right, because we're just multiplying by 100, which is the same thing, we would get 418 joules of energy needed. And so molecules with stronger IMAFs will have A, higher heats of vaporizations, B, higher heats of fusion, C, higher boiling points, D, higher melting points, E, higher viscosity, higher specific heat, which is F, or higher surface tension, or all of them. And so this question is pretty easy, because all you have to do is find that if 2 are correct, that means they have to be all of them, because if 2 of them are correct, we can't just pick one, so it has to be all of the above. So if you think about IMAFs are those attractions between molecules in a group of molecules. And so there's, remember, 3 types: hydrogen bonding, dipole-dipole, and dispersion. And so if we have more attractions or stronger IMAFs, it definitely has a higher heats of vaporization, or this just means it has a higher boiling point. So if it has higher heats of vaporization, because the attractions keep it together, and so it doesn't want to evaporate and turn to a gas. And also, stronger IMAFs do increase heats of fusion, or how much energy we need to melt it, because again, solids have IMAFs too. And so if there's more IMAFs holding them together, again, they don't want to be in a liquid. So once we know A and B is true, C and D are practically the same as A is the same as C, because heats of vaporization are the same thing as boiling points, and heats of fusion are the same thing as melting points. And so these four are all true. So just from figuring out that A and C are the same or B and D are the same, you could have deduced that all of them are correct. But let's just go through and talk about each one just to make sure you know it. So higher viscosity is true because if we have IMAFs, think about viscosity. Viscosity is a liquid's resistant to flow, so it doesn't want to flow fast or slow. So if you have more attractions between the atoms, they will clump together. And so if you ever have something like salsa, something chunky, or with a lot of clumps, then it's hard for it to flow. But same thing with IMAF. So if you have stronger IMAFs holding it all together, we would have a higher viscosity. So it'd be harder for the the liquid to flow. And then definitely higher specific heat capacity because we talked about how water has so many IMAF, so it holds up all the water together. So when there's heat applied, it has to first break these IMAFs in order for it to change temperature. And then G, higher surface tension is also true because if we have more strong connections, or more like let's just say we have like strings supporting some weight. So if we have a lot more strings, that means it can hold more weight. So like let's just say we have 3 strings supporting a 10-pound dumbbell. And so if we have even more strings, like maybe like 10 strings, the strings can hold it more and support more weight. So IMAFs, just like how ropes can hold weight if we like make like a net, the more IMAFs or connections we have, the more we can hold. And so that is why water has all of these characteristics, pretty much except viscosity, which is weird, because water has a lot of IMAFs that hold them together and keep it compact, and that's what makes water so special. So that is it for today. So today we talked about specific heat. We talked about heating curves and cooling curves, and so those like little stair-stepping charts. And then we also talked about how heat and thermal energy flow from hot to cold always. And so I hope that helped you explain about heat, calorimetry, and heating curves. And so the next video will be all about phase change diagrams, and we'll talk more about that on the next video. And so phase change diagrams have to do with all this stuff, so we're just going to synthesize it. And so again, I'll see you later, and I hope you have a good day.